Hi, welcome to the session of back EMF and significance with respect to DC motor. So, significance we'll discuss later. So, let us think what is this back EMF? So, in a DC motor, as I explained the principle of operation of a DC motor in the previous session, there are flux in the armature and the main field. When the flux interacts, armature flux and the main field flux interacts and the force is exerted on the conductor, motoring action takes place. After this motoring action, the conductor starts rotating and the armature conductor will cut the magnetic flux which is between the north and south pole. So there is a generating action existing in the motor. So inside this, so after the motoring action, we have a generating action. So according to Faraday's laws of electromagnetic induction, there will be an EMF induced in the armature conductors when the rotating conductor cuts the magnetic field. So the EMF induced will oppose the cause producing it. So the cause here is the supply voltage which is producing the back EMF. So in a DC motor, electrical input, that is the supply voltage is the cause, as I said, for the armature current and the motoring action, and hence the induced EMF opposes the supply voltage. So EMF tries to set up a current through the armature which is in opposite direction to that which supply voltage is forcing through the conductor. So as this EMF always opposes the supply voltage, it is called as back EMF and denoted as EB here. So the magnitude of this EB is given by EB is equal to P phi NZ by 60A, where P is equal to number of poles, phi is flux produced by each pole in Webers, and N is the speed of the armature in RPM, and Z is the total number of conductors of armature conductors, and A is the number of parallel paths in which Z number of conductors are divided. So A is equal to P for lap type winding and A is equal to 2 for wave type winding. So the back EMF is always less than the applied voltage. Hence, the armature of a DC motor can be represented by a back EMF. So EB in series with the armature resistance RA as shown in the figure. If you look at here, this is the EB is in series with RA and EB is always less than the supply voltage. So this is the equivalent circuit of this motor which is symbolically represented here. Now coming to the significance of the back EMF. So back EMF, if you take the equation, EB is proportional to N phi. So where P Z and 60A are all constant. So EB is proportional to N into phi, where N is the speed in RPM and phi is the flux produced per pole. So during small loads, now if you take an equation, IA is equal to V minus EB by RE. So for small loads, IA will be very small. So IA will be very small. So if the speed is less, if the speed is less for high loads, then EB is small, hence more current flows which develops torque. So we find that EB acts like a governor. It controls the current. Depending on the type of loading, it controls the current. So due to the presence of back EMF, the DC motor becomes a regulating machine. That is, motor adjusts itself to draw the armature current just enough to satisfy the load demand. So the basic principle is, as I said, EB is proportional to N. Okay. So when the load is suddenly put on, so it is increased to the motor. Motor tries to slow down. So as you increase the load, the speed reduces. So the speed of the motor reduces, due to which back EMF also decreases. Therefore, the difference of this voltage V minus EB also increases and motor draws more armature current when suddenly the load is put on. Now, if you take in other way, when the load is suddenly decreased, the speed of the motor tries to increase. Therefore, the back EMF increases and the difference of this voltage V minus EB will eventually decrease. Therefore, the current Ia also decreases when in the load on the motor is decreased. So, the motor speed stops increasing when the armature current is just enough to produce the less torque by the new load. So, due to this, increase and decrease in the armature current, force experienced by the conductor and hence torque on the armature keeps increasing and decreasing depending on the armature current. So the increase in the torque is just sufficient to satisfy increase in load demand when there is Ia is increased. So Ia is proportional to torque. As we know, the torque equation also, Ta is proportional to phi Ia. Therefore, torque increases when armature current increases when load is suddenly put on the motor. Thank you for watching.